The next talk is given by Richie from Düsseldorf. He is presenting part of the work done in project C7 together with Stefan Egemer. And Richie is discussing colloidal motion in static and dynamic random energy landscape. Okay. Yes. Yes, it does.
Good afternoon, ladies and gentlemen. I'm a PhD student in the group of Stefan Egemer. I would like to talk to you briefly about some of the work that we've been doing in dynamics in central energy landscapes. Firstly, very importantly, a few acknowledgements. I'd like to thank Florian Evers for doing the two experiments and very kindly giving me the data and visualizations. Michael Spielberg, Hartmut Löwen, there we go. Hartmut Löwen and Jürgen Horbach for helpful discussions with the theory and analysis, and Natalie Clark for help preparing the presentation. Also, I'd like to acknowledge financial support from the Mary Curie Early Stage Training, the Biosoft Town School, and of course, the SF Group. I'd like to start with a macroscopic example of how energy landscapes can affect motion of objects moving through them. And this is something which I haven't personally done the experiments for, not purposefully, and I wouldn't recommend doing repeated measurements because no one likes whiplash. But it is clear to say that the energy landscape does slow down the particle moving over the car moving over these objects. This is actually in America. Düsseldorf not quite as bad as that. For a more microscopic example, I'd like you to consider the energy landscape of a glass. And so what does this mean? Well, how does a glass have an energy landscape that's just a collection of particles? Well, essentially the coordinates and momenta of each particle define a point in this configuration space, each of which point has an energy. And you can consider the evolution of the glass as a single point moving through a rough energy landscape. That's kind of represented here in a very simple schematic way, where this is the coordinate space and this is then the energy. What you can see here, in this case, is that the glass actually is a very deep minimum, and so if the system is in a glassy state that sits here, the crystal you can see over here is an even narrower but slightly deeper minimum. And what the energy landscape then does is it means that it takes a very, very long time for the system to move from this glass to essentially anywhere else. So the energy landscape is then imparting a very, very long time scale onto this system. The dynamics is slowed down a lot. What you don't see here is that actually when any constituent part of the glass moves, it's also changing the landscape. So not only is this a complex energy landscape, it's also a dynamic energy landscape. And people are trying to understand the structures and features of the energy landscape to help understand glasses as a whole. What we've done is we've actually created an experimental model system where we can create rough dynamic energy landscapes in a controlled way and look at the actual dynamics of real particles moving over them in experiments. But how do we do this? I'm not going to go into details too much because Kishan and Paddy already talked about holographic optical tweezers. Essentially what we have is a holographic optical tweezer setup, and we generate light fields, and particles move to regions of high light intensity. So if you have a light field and plot a particle to the right refractive index, the particles essentially move into regions of high light intensity. So doing this, we create our light fields. This is how I essentially generate this little SFB advert here, which I think would be quite nice. I just threw that one together. That's 4 micron polystyrene particles in water. There's also two very interesting posters that I can recommend you looking at. That's the poster by Christoph and Jörg, which both talk about different applications of light fields in the colloidal realm. Wholeheartedly recommended. Okay, so what do we do? What are these energy landscapes that we make? Well, I want to talk about 3 experiments. The middle one is quite dark, I hope you can still see. On the left is a one-dimensional energy landscape. In the middle is a 2-dimensional energy landscape. This region here you can actually see essentially should be green, but the contrast isn't great. And at the end we have a one-dimensional energy landscape which is then changing in time. So I'm going to go through all of these, but I'll start with the simplest case. This is the 1D landscape. First of all, what do you see on this slide? Well, this is the light field which we generate holographically and project into the sample. You can see, first of all, it's not smooth, it actually has an inherent roughness. The 4 rings are actually not related, they're just so we do 4 measurements at the same time to improve statistics and speed. And the spot in the middle is the zeroth order spot, which will be familiar to anyone doing holographics. What we actually do is we trap a particle in that spot, and we use it to monitor the overall motion of the light field. Okay, so we project that into our sample. These are 1.4 micron radius polystyrene particles. I've overlaid the light field in this black dotted line so you can see kind of where it is. Normally, of course, you wouldn't see it, and you can see the coordinate here is x. So then what we do is if we collect lots of these images, and we link them together, we can then determine the probability of the particle being at a certain point in time. So we can generate this probability function that the particle is at x at a certain time, for the probability of part is at x. Then using the Boltzmann relationship, we can generate from this the energy landscape. So we can actually look at the energy landscape felt by particles. And this is quite nice. I've never actually seen this in a glassy place where you can actually look at the actual energy landscape. So this is actually quite nice here. What you can see on the left is the energy in kT, and across the bottom is the position scaled in units of the particle radius. This is the characteristic length of the system. You can nicely see the maxima and minima and kind of roughness of the landscape. If you look at the distribution of energies, you get this Gaussian distribution, which has a width of 2 epsilon. Epsilon is going to be our control parameter, which we can modify by increasing the laser power. So if we make the laser field stronger, this essentially just gets wider, and we can make these minima deeper. Okay, so how does this landscape affect the particles of dynamics moving around this ring? Well, I'm going to go to the trusty mean square displacement. I hope you're all familiar with it, but very briefly, this is a time axis. This is a position axis here and a time axis across the bottom. So short times, there we go. Short times are down here, long times are up here. On this graph, normal diffusion is represented by this dotted line, which is a diagonal line. And what you can see is that as we increase epsilon, so we increase the strength of this roughness. At short times, nothing really happens. At long times, we move further and further away from normal diffusion. So we also did some relatively simple Monte Carlo simulations. And I think you'll agree that the agreement is very good between the experiments and the simulations. I was quite pleased when that actually happened. That's nice. No foot parameters or anything, just straight up. So that's good. These measurements, 1,000 Browning times is about 10 hours, so in order to extend to longer times, I then did some longer simulations. And these are basically the same, but now you can see we go up to about 1 million Browning times. So essentially the same figure, this is now just pure simulations. I mentioned that these dynamics move far away from the diffusion case, and to quantify that, what we did was essentially take the derivative of this logarithmic plot, which is also the diffusive exponent. So in normal diffusion, this mean square displacement grows linearly with time. For subdiffusion, it grows with time to this mu, where mu is less than 1, and for superdiffusion, mu is greater than 1. So in this plot here, we just plot mu as a function of time. And what you see is this line here is in diffusion. And you can see for the increasing epsilon goes this way, but initially at short times it drops superdiffusive down to a minimum, and then there's a very slow return to diffusion. I'll come back to that in 1 second. The last graph I want to show on here, sorry for the people at the back, I know you can't really see the bottom of the screen, but I hope that I can describe it to you in words as well. This last one is then the diffusion coefficient as a function of time. So this is kind of the instantaneous diffusion coefficient, basically taken from this plot up here. What you see again is for increasing epsilon, this gets deeper and deeper and deeper. Diffusion on here is a horizontal line, and the position of this horizontal line then marks the long-term diffusion coefficient. The theoretical values by Schwanzig, he was a very, very smart guy. He did so much stuff. There's already a famous equation by him earlier today. This was in 1988. He predicted this exact relation, that the long-time diffusion coefficient should be eta minus epsilon squared. What you see for the smaller values of epsilon is that the agreement between the simulations and the experiments and the theory is actually very good. And for the largest values of epsilon here shown, it doesn't quite get there. Okay, so what we wanted to ask in this case was, how long does it take to get to diffusion? And actually, as far as we could tell, so looking to the literature, I may well be wrong, but from looking at the theories, I couldn't find any specific thing which told me for this system, how long does it take to become diffusive again for a given value of epsilon. So we basically did some basic fits, and what we find is that if you extracted timescales from these plots, so this is the time it takes to get back to the function, we essentially see this timescale goes as epsilon, the exponential of epsilon squared. Interestingly, 1 over the long-term diffusion coefficient. We need to look into that a little bit more, not quite sure. This was basically, I fitted these data on Friday, so this is also new data. Okay, so this is how a landscape can generate a very, very long time scale, as in glasses. How does then the topology of the landscape affect the dynamics? Well, now I'm going to move on to the 2D case. So here you can see, I mean, you can't really see this is essentially just a rough landscape, a rough optical landscape. Here you can see the red area is where the light was projected onto the samples, and the black lines are particle trajectories after they contract. So you can see outside the light field, these are quite large, this is just normal diffusion. Inside they're much more localized, so these are being trapped by the landscape. And this wonderful figure here is what you get if you take just the light intensity and you convolve it with a particle volume. So this is the light field as seen by a particle. And what you can see is the really nice maximum, minimum, and the kind of the richer structure of this landscape compared to the 1D case. Okay, so how does that then affect the particle dynamics? Well, I'm going to show you again the 1D experiments, just for comparison, and here we can see the 2D measurements on exactly the same scale. In this case, it's just as a function of r rather than x. So what you see is it's relatively similar. For increasing epsilon, you get further and further away from diffusion. However, in the 2D case, at long times it seems like it's actually parallel with the diffusive line. So you actually see that the return to diffusion is much quicker. And in this case, you're still moving away from this line, as even at the longest times from these measurements. If you think about this for a second, it kind of actually makes quite a lot of sense. In the 1D case, to be diffusive, you essentially have to find and overcome the deepest barriers in the system. There's no way you can actually be completely mobile until you found and overcome the deepest minimums that you can't overcome it. In the 2D case, you can essentially just explore the valleys, so you can explore most of the landscape without ever having to cross a big barrier at all. So you can essentially become very mobile without ever having to actually cross a big barrier. So here, just from the topology of the landscape, you can see that this long time scale has essentially disappeared. And you can characterize this again with this diffusive exponent. So this is the 1D case, just from the experiments. You can see this then is not quite as good statistics as the simulations, I'll grant you that, but it's still pretty good. You can see this long time tail where it's not returning to diffusive behavior. In the 2D case, already after 100 grounding times, for all landscapes, it's essentially become diffusive again, purely from the topology of the surface. Okay, so the last little experiment I'd like to talk to you about is, this is my nice little animated GIF. Didn't put any movies in, just use animated GIFs. The last one I want to talk about is essentially the same as the 1D case, but now instead of having it static, the nice thing about the holographics is if you try and generate a smooth landscape, it turns out to be rough, which was useful for these experiments because that was what we were planning all along. It's actually also easy to generate different realizations of the roughness. And we can then project them with a different frequency into the sample. So we essentially have lots of different 1D landscapes with the same epsilon, we project them to the sample with a certain frequency. The question then is, how does the dynamics of the landscape affect the particle dynamics moving within them? So we'll go back to our trusting sphere displacement. What you see here is this is then the frequency, so this is a very low frequency. You see something like the static case. As you then increase the frequency of the cycling, you get still subdiffusive, 0.25 Hertz, we're now actually super diffusive. 2 Hertz, we're getting close to diffusion again. 15, we're essentially then back to diffusion. If you plot this on a graph like this, what you see is that this is frequency down here, and this is somehow the mobility. Down here, this is our static limit, so this is where these system particles float down by the landscape. Up here is where the cycling frequency is so fast that the particles don't have time to respond, so they essentially integrate with time and they see a flat landscape. And what you see quite nicely in the middle is that at a certain frequency, you actually get a peak, so you're actually driving the particles faster. And this is due to, if you imagine if you just turn on a landscape, some particles will be at a minimum, but on average, most particles won't be at a minimum, so most particles will roll down to the nearest local minimum. If you then change the landscape just before they reach that minimum, then they essentially will now also be not in a minimum, most likely, and they'll keep rolling down. If you change just the right frequency, you essentially drive the particles by this random landscape. Again, this was actually collected on Wednesday, so this was, I think, what was it? Wilson's on Friday, Havlick on Thursday, so I'm third in this case. I actually did this measurement on Wednesday. So this is quite raw data, and we're going to investigate what happens as you change laser power, but I think you'll agree it's an interesting effect. To conclude, I would like to say what we've done is we've essentially managed to create potential energy landscapes in multiple dimensions in a controlled way, whilst we can actually image the landscape, look at how the particles respond to it, and do all this in a real space situation. The simulations, which are relatively simple, are an excellent agreement, which is very helpful because it means we can extend to much longer times. And the long-time asymptotic behavior agrees with the theory, which is a great check, and also it's very nice to suggest that things are working well. This quantification of the intermediate timescales, if anyone knows of theoretical models which predict these timescales, that'd be great. Otherwise, we're starting to do that, which is also a wonderful thing. And this new effect, which I don't think has a name just yet, is this with a cycling random background. It's certainly not stochastic resonance, because that's a whole different thing, but it has some stochastic elements and it's somewhat resonant, but we're not quite sure yet. But that's actually very interesting, I think you agree. There's one other caveat which I'd like to mention, and that is that the dynamics of a landscape are generally controlled by the deepest minimum in the landscape, which is found by this unfortunate driver in America when she drove into a potentially deep minimum, not knowing how deep it was. The take-home message here is that this car, stuck in this minimum, isn't going anywhere for a very, very long time. So, I'd like to thank you all for your time, and I hope you enjoy the excursion.
Okay, thanks for the talk. Are there some questions?
according to the resonance you see, does this resonance frequency change if you take different particles?
It's a very good question. It probably will. There's multiple effects that go on there, because as you change the size of the particles, you change the interaction with the landscape, because the interaction with light goes as the radius cubed. So you would see an effect that this probably becomes less prominent with smaller particles. And you also change the correlation length. It would definitely change. It would almost certainly change to a higher frequency with smaller particles, but I'm not sure. It's a good question, and it's something that I need to try when I do, what is Wilson say, next Friday, or maybe the Friday after. A good question.
Albert?
Question about, isn't your landscape going to be mixed up somewhat if two parts are close together with the scattering?
So that's a good question.
You could refer it also more, so does it become more complex?
It would become more complex with more particles. We actually work with a regime where essentially we have completely dilute particles. In the analysis, I would actually remove trajectories if they came too close to each other. I imagine in this case, in the 1D case, if you add more particles, you essentially get to single cell diffusion in the end. In the 2D case, we would like to look at actually then increasing the volume fraction in the 2D landscape, because then it may be the case that particles pull each other over different areas.
I was more thinking about along the lines of talk to the right here, the scattering of the one part.
Optical binding. So optical binding, that's a very good point. Optical binding, I'm not sure, maybe I'm wrong in this, but I find optical binding, you need relatively high laser powers for optical binding. No? But you need relatively small interparticle separations, if I'm right.
Yeah.
Typically. So in this case, I can show you a picture real quickly.
But you have here a minimum of several 8 kT or so. So
yeah,
that means the field is quite strong.
It is quite true, but then
the scattering of one particle, if it hits the other, is already going to give this.
Yeah, that's true. So in this case, actually, you see that in the energy landscape, because this energy landscape is now not just optical, but this is actually based on those particle positions. So if you saw that effect, we would see it here. And secondly, I hope you can see that the distance between particles is essentially very small. So even if we were getting scattering from particles, I would essentially, just by diluting the system, I've kind of tried to get rid of that.
There is time for one more question. Yes, Arnold?
So, comment, I think your work nicely shows that this one-dimensional energy landscapes, which you showed in the first slide, which are sometimes taken as caricatures of glasses, are very, very dangerous. If you have a two-dimensional landscape, it's completely different. If you have an n-dimensional landscape, So this picture is taking this
absolutely
grain of salt.
It's interesting that the mean square displacement of these bony landscapes actually looks so similar to glasses, which is kind of strange. So I haven't put it here, but you do kind of get a very similar behavior with the slowing down and obviously very long time scales. In the 2D case, so as you increase the dimensions of the landscape, you would expect it to get, the glassy energy landscape obviously is many, many dimensional, so you'd expect it to get closer, but what I think is it gets further away. So somehow here it seems that 1D is, in terms of just the mean square displacement, obviously I'm not saying it's the same, but the mean square displacement looks similar in a 1D, more similar in a 1D energy landscape than a 2D energy landscape. But you're right, it is dangerous.
Okay, then we would like to thank you again.